Good evening, everyone. Welcome to live session of a course of Mechanics of Material 2. So, my name is Vaibhav Gupta, and I'll be teaching solving some sample problems for the week 2 session. So, going ahead with this lecture, in week 1, we studied concepts in mechanics of material. So, basically, in week 1, we studied that 4 basic concepts which involves force, displacement, strain and stress. So in the lectures we have seen that we cannot relate force and displacement directly, hence we require 2 additional quantities which will deal with the geometric dependence and the material dependence of the body. So hence we require stress and strain. Now displacement and strain are related by displacement strain relation, whereas stress and strain are interchangeably related by constitutive relation, while force and stress are related by equilibrium equation. There is one more equation which relates strain to displacement, that is compatibility condition. Now in the week 2 lectures, you have seen the definition of each and everything one by one and in depth. So starting with this week 2 summary, first of all, I will provide you the summary of week 2 lecture, what has happened in the week 2. And finally, hello, Arnav, are you able to hear?
Sir.
Okay, so just I started the lecture. So what I told, like in week 1, we saw the basic concepts to be covered in mechanics of material. So in week 1 we saw that 4 concepts are there, which
सर,
is
आज भी कोई नहीं ज्वाइन हुआ है क्या?
Yeah.
सर एक क्वेश्चन था मतलब अगले असाइनमेंट का.
Okay.
उस क्वेश्चन में सर ये जो एक मतलब आप जो क्वेश्चन नहीं पढ़ाए हुए थे लास्ट में कि यू ए मतलब ए बी सी डी दिया रहेगा.
Yes.
और तो उसमें सर क्या कहते हैं, मैं एक बार उस क्वेश्चन को आपको मेल करूँ मतलब इनबॉक्स में डालूं क्या?
हाँ, इनबॉक्स कर सकते हो. जो डाउट सेशन डाउट फॉरम है ना.
अरे सर इसमें ये क्या कहते हैं चैट में कॉपी पेस्ट कर दूं क्या?
हाँ, कॉपी चैट पे कॉपी पेस्ट कर दो.
सर एक्चुअली बात वो यहाँ थी ना कि सिंपल उसमें सर क्या कहते हैं आपका यू और EX EY और EZ = EZ दिया था, ठीक?
ओके.
और उसमें सर UX आपका दिया है 3EX + 2EY + 3EZ.
ओके.
तो सर हम जो EX दिया है, EX के लिए UX के लिए ये लिख सकते हैं ना U.EX.
क्वेश्चन भेजोगे तो मेरे को एग्जैक्ट समझ में आएगा.
एक मिनट सर, बस एक मिनट में भेज रहा हूँ क्वेश्चन. सर एक मिनट, 2 क्लास चल रहा सर एक ही साथ.
Basically, what I am saying, like you just post the question in the mail ID because I have to continue the lectures because other people will see after the link will be posted. So it's better to not delay the lecture. You mail me or in the doubt forum you put the question. I'll mail you after this lecture. Okay.
सर मैं ये चैट में डाल दिया.
Okay. So I'll check with this question. Okay, and after the lecture I'll get back to you. Is it fine?
Okay.
So we'll continue with the lecture.
Yes, sir.
Okay. So basically in week 1, what I was telling, like we covered 4 concepts, like the relation which will be used in mechanics of material is force, displacement, strain and stress. The force and displacement can't be related directly, so we need additional 2 quantities, that is strain and stress, which will give us the dependence on material and geometry of the body. So the stress and strain are related by the constitutive relation. The stress and force are related by the equilibrium equation. Whereas we relate displacement to strain with the help of displacement and strain relation, and strain to displacement with the help of compatibility condition. So now in the week 2 lectures, we have seen each of these in a brief manner, that what each term means. So first I will give you the summary of what happened in the week 2 lecture. So first of all, in week 2 lecture, we go with the first concept, that is force. So the force is nothing but a mathematical concept. First thing. Second, we cannot know the force. We can't measure force. So what can we measure? We measure displacement. So what is the example? Like if we push a wall, we don't know how much force we are applying. Just we can see the displacement, that what is the wall is having a displacement in a minute scale. We cannot see in a naked eye, but in a minute scale it's it's getting displaced by some amount. So we can't measure force, we only measure displacement. So next question comes, is force a scalar or vector? Is force a scalar quantity or a vector quantity? So force is a vector quantity. Why? Because it follows vector law of addition. Okay. So in the lecture also, the example has been given with the spring wave balance system, in which three spring wave balance are connected like this, and it shows some reading like 20 Newton, 40 Newton, and suppose it's showing 60 Newton. So this is the main balance. So we cannot add force simply like 20 Newton plus 40 Newton plus 60 Newton. This is wrong. We cannot say that a total force acting is 120 Newton.
Yes, sir.
We have to just project this 40 Newton to this angle theta in same direction, and then we have to find out the force. That's why we say that force is a vector quantity. In scalar quantities like mass, suppose the mass has been given, we can simply add the mass without having seeing the direction of this thing. So mass is a scalar quantity, whereas force is a vector quantity. Understood this thing?
Yes, sir.
So this is what we meant by force. So second concept which we'll see like is displacement. So basically to go into the displacement, we need to understand certain things, that what the body is, okay, and how it is idealized. So body is nothing but is a set of ordered, countable / countless particles. Okay, so here these three words are there. What is three different words? What is countable, what is ordered, and what is countless? So order is nothing but, suppose I will give you one example which was given in the lecture also. Like suppose this is point 1, this is point 2, this is point 3, this is point 4, this is point 5. So if we take 1 as a reference, what we'll say to point 4? That point 4 is in front of 1. What is point 5? It is in the backside of point 1. What is point 2? It is in the top of point 1, and 3 is in the down of point 1. So this is what means by an order. Okay. Yes. Now second thing is countable and countless. So suppose if I will say that you count the integers from 1 to 100, will you be able to do it? The answer is yes. We can count 1 to 100.
Yes, sir.
But whereas if I will say that tell me how many real numbers are there from 0 to 1, say, can you count?
No, sir.
The answer is no. So this is the basic difference between a countable and countless thing. So in our course, like in mechanics of material, we study body to be ordered countless particles, made of ordered countless particle. Okay. So how we define? So this we also know, this we also say as continuous system. Okay. And for ordered countable particles, if a body is made of that thing, we'll say as discrete system. Okay. So I'll give you some like notation wise how we'll define body is. Suppose a body is made up of XYZ. Why I'm always taking XYZ? Because to define a body, we need three coordinate system like up, down, right, left, top, bottom. Okay. This is how we define a body. That's why we use always XYZ. So suppose I'll say the body is made by XYZ in which X varies from 0 to 1. Also Y varies from 0 to 1. And Z varies from 0 to 1. So what it mean? So we'll draw a cube. Okay. So suppose I'll say so this is a cube and this is X, Y, Z. So all the points inside this cube, all the points inside the cube will say the body. Okay. This is what the body represents. This is a continuous system. Whereas if I have to define the body in a discrete system, how I will represent? Where X belongs to 0 to 1, Y belongs to 0 to 1, and Z belongs to 0 to 1. Here there are not n number of particles. It's a set of particles. Just like 0, 0, 0, X takes value 0, Y takes value 0, Z takes value 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, then 1. So these are the number of particles which will be in the body, not the whole body inside the cube. So suppose if we draw again that cube, so this all points represents that body, not the whole body. You get the point?
Yes, sir.
So this is what the discrete representation of the body and a continuous representation of a body is. Now going along that further, now suppose I will say like my Cartesian coordinate system is like this. Ex, Ey, Ez. Okay. So suppose I have a point. Okay, I have a body. So I denote this body by this. So this body is at time equal to 0, suppose I'll say. At time equal to t0, this body is like this. So the can you say like if two different persons are there, they can put the same point here? They can do in any way, no?
Yes, sir.
They can map the physical body at any point space depending upon their system.
Yes, sir.
So we define one term which is called as placer. This placer is nothing but it maps physical body to point space. Okay, with the help of placer, we map our physical body to a point space. Now this point consists of some points. But again, is it unique? Depending upon different coordinate system, anyone can give any number of points to that body, any set of points.
Yes, sir.
So this is not unique. So now we map this body from point space to a vector space. Then how we do this thing? We just put a reference. Suppose I define this as 0, 0, 0. So now I have mapped the body from point space to a vector space. Okay.
Yes,
This
sir.
is known as configuration. Okay, these two words are very important if you go ahead. So one is placer, one is configuration. So now the body is at time t equal to 0. So what we call this body as? We call this body as in the reference configuration. Okay. This configuration is referred as reference configuration. Okay. Now suppose the body at time equal to t equal to 0, it moves to some other this point. Now x is that point at t equal to t. So again we'll map that body from point space to vector space. Now we say that this configuration is current configuration of the body. This is the current position of a body at time t equal to 0. Okay.
Yes, sir.
Now when we map the reference configuration body to a vector space, we denote it by capital X. Vector capital X. Okay. And when we map the body from current configuration to from point space to vector space, we say as small x. Okay. Can you tell me what is the displacement of these two bodies? Displacement is nothing but a straight line joining the position of a particle in the reference configuration and current configuration. That is the shortest line. This is the displacement.
Yes, sir.
So what do we mean by displacement? Displacement. It is nothing but
Higher position by nothing.
a straight line joining the position of. Now high and lower, you don't know this thing. You know only reference and current configuration. These are the technical terms. Okay. Position of the particle in the reference configuration and current configuration. Till here all things are clear. See, suppose we have a body. Suppose at time equal to t equal to 0, it maps from 0, our reference point to existing space. We denote it as reference configuration capital X. Now at time equal to t, it goes somewhere. We again map to our reference base and we say it's current configuration, like position vector of the same particle in the current configuration.
Yes, sir.
Okay. So what is the displacement? The straight line that joins the position of the particle in reference and current configuration. Okay.
Yes. Yes,
Now
sir.
you see this figure, this triangle. What this triangle shows you is nothing but a. Can you see vector law of addition here?
Yes, sir.
So what is u here? Small x minus capital X.
Yes, sir.
Or else what have you learnt, like capital X plus u equal to small x. Both are
Yes,
same.
sir. Yes, sir.
Okay. So our displacement is nothing but u equal to small x minus capital X. This is the displacement. Okay. This is displacement. This is current configuration. Remember, all these are vector. This x underscore means it consists of three points: ex, ey, ez. Whatever the configuration you are taking. Okay. This is reference configuration. Now after this, you learn one more term like we can relate our current configuration to reference configuration with the help of a deformation field. What is that? That this small x can be related to capital X. Capital X is always reference configuration. You remember, wherever the capital X is written, it will represent as reference configuration. And wherever we write in small letters, it represents the current configuration. This is how we follow in the course. Okay, and you will find in the books also, textbooks. So this X, this it is nothing but a deformation field which relates the current configuration with the reference configuration. This is known as deformation field / motion field. So in this course, we mostly refer this X as deformation field. Why? Because these two are changing in terms of positions. When the time will come, that we have to include time also. We will use the word as motion field. Okay. This X,
small s.
yes.
Sir.
Yeah.
नहीं सर कंफर्म हो गया तो क्लियर हो
Confirm. Okay. So this
Yes.
X is nothing but a function of position vector and this T. So only when it's a function of cap X or small x, whatever, it is known as deformation field. Okay. And when it
Yes, sir.
depends on both time also, then it becomes a motion field. Got this point?
Yes, sir.
Now the property of this deformation field is that it's a one-to-one function. What do we mean by a one-to-one function?
Sir, EX, UI, and EZ.
No, one-to-one function is that every point has a domain, has its range. Okay.
Okay.
So each particle which will be having some domain will definitely have the range and a vice versa. Okay.
Yes.
So it is referred to as one-to-one function. So the property of one-to-one function is if a function is a one-to-one, we can take an inverse also. So now here, like if small x is related to capital X like this, we can relate capital X to small x with the inverse of this. Okay.
Yes, sir.
Because it's a one-to-one function. It gives us the liberty to do this thing. So now suppose U is small x minus
Sir,
capital
ये
X.
Small x one-to-one function कब show करेगा?
Small x it's like a unique thing. Wherever a particle is taking some position at time t equal to 0,
Okay.
it gives you three different things like Ex, Ey, Ez vectors, position vectors. Okay. Now to relate this small x to capital X, you need a deformation field. How will you relate? Like how to relate particle who is having current configuration, suppose some values.
Yes.
So what are these reference values? You want to know. How will you know this thing? You will know with the help of this function.
Okay, sir.
We'll solve one example, you will get to know better. Okay.
Yes.
Okay. So now we saw like displacement is small x minus capital X. This is what we saw with the help of vector law of addition here. So now suppose suppose you know only small x, you don't know capital X. So how will you define this small u? You will say I'll use the deformation field and convert this capital X into small x. You can use this thing.
Yes, sir.
Similarly, if you know capital X and you don't know small x, what will you do? You will again use the deformation field. Okay.
Yes, sir.
You can write like this. Now, if you are writing the displacement in terms of current configuration, this small x represents current configuration. This thing is clear, no?
Yes, sir.
So this is known as spatial representation. Or Eulerian representation. When a displacement field is related by current configuration. Okay. And when the displacement field is related to the reference configuration, it is known as material representation. Or Lagrangian representation. Got this thing?
Yes, sir.
Any doubt so far?
No, sir.
Now we'll solve one problem here. Okay.
Yes, sir.
Now suppose a body in the form of a unit cube is given by this. I said you like we'll define body like this in the continuous representation. Like body consists of x, y, z particles, where the x particle varies from 0 to 1, the y particle varies from 0 to 1, and z particle varies from 0 to 1. It will form a cube that I have drawn earlier, similar like type of cube.
Yes, sir.
And it said like in the reference configuration, you can see that the letters are in the capital form. You can see?
Yes, sir.
That's why it is mentioned in the question in the reference configuration.
Yes, sir.
It's subject to the following deformation field. He said. In the question it is said like
Yes,
in the subjected. So the deformation field is given like this. These three are given to you. Now you can see that small x is related to capital X, small y is related to capital Y and capital Z, and small z is related to capital Z and capital Y. Okay. The question he has given that you have some particle in the reference configuration, and he has given you some relation for the how to relate to the current configuration. Okay.
Yes.
Now he's asking, he said that A is the constant, and XYZ are the capital XYZ are the Cartesian coordinates of the material point. So material point is the points which refers to current reference configuration known as material point, and the points which refers to the current configuration known as spatial point. Okay.
Okay.
So and small xyz are the Cartesian coordinates of the same material point after deformation. Okay.
Yes, sir.
So first thing he asked, determine the displacement vector components in both the material and spatial forms. Okay.
Yes, sir.
After going to this question, do you find some idea how to do it?
Yes, sir. सर ये
How
ब्लू
will you
नहीं हो
proceed?
सकता मतलब और फुल स्क्रीन में
फुल स्क्रीन में नहीं होगा, ये टैब में इतना ही रहेगा मैक्सिमम, लाइक मैं इसको इतना कर सकता हूँ मैक्स.
ओके ओके सर कोई नहीं. सर ये असाइनमेंट मतलब क्वेश्चन असाइनमेंट का है कि आप अपने साइड से इसको
मेरे साइड से पर असाइनमेंट में हेल्प होगा. माय जॉब इज टू हेल्प यू टू डू द असाइनमेंट करेक्टली.
सर एक और क्वेश्चन था, मतलब इस कोर्स में कितने लोग मतलब कितने स्टूडेंट हैं, क्योंकि अभी सर अब मैं इससे पहले फ्यूलिड को ज्वाइन किया था, उसमें काफी बच्चे थे, तो मैंने फ्यूलिड वाले सर से बात करके मैं इधर आ गया हूँ. इसमें अगला मतलब पहला वीक का भी देखा तो मैं अकेले था और इसमें भी अकेले हूँ.
They are like here in this course total is the persons are like around 700. So the point is like this, like you like people don't have like clash also in classes also. So they afterwards they find like they ask us about the YouTube link and they see the video for that. Okay. So our purpose is to solve the sample problems which will help you to do the assignment correctly. Our purpose is to help you with understanding the concept better, which are covered in the week's lecture. Okay, and you have a one-to-one talk also with me, like whatever you have doubt. Now the things are very simpler. Like you can find out that okay, the things are getting into the picture. You also getting to know all these things. But when the course proceeds, certain things will be there which are complex, and sometimes you need a help from someone else that which will guide you better. This is what the full motive of this course. Okay, if you will join, you will learn better. You will have a you will talk to me one-to-one just like you are doing now. Okay. If you won't join, you will just simply see the lecture. Okay, this is what I am doing. If you have some other doubts, also you cannot convey it to it, or you cannot get a live thing. That is what the live session means actually. So in our time also we do like that also. So it helps us like wherever you go in the future. No, it will help. It's hard like people are not joining, but I can't help it with this thing. Yeah. So anyway, going ahead with the problem. So you understand how a body can be represented. Okay. Now similarly, in the question it is given that you have given the deformation field. Okay, 1 second, I'll add one page. So in the question you are given a deformation field. You understand the word different deformation field?
Yes, sir.
So this is the deformation field given to you. Okay. Now in the first question they said determine the displacement vector in both the material and spatial forms. So what do you mean by material form? Material form means you have to find the displacement in the reference configuration.
अच्छा, reference मतलब 0 point.
No, reference means capital X, capital Y, capital Z.
वही capital X.
Where the body is at time t equal to 0.
वही
Okay.
सर बोला हूँ, time t
Yeah.
equal to 0.
So U is, we know U is small x minus capital X. Now first thing you have to find U in terms of
Yeah, is
material
small
form.
x.
First we'll do for material form.
Okay, sir.
So now how you will know? You just need to convert small x into capital X vector. How you will do it? With the help of deformation field.
Yes, sir.
You use this thing. So
Yes, sir. सर ये स्मॉल एक्स है, U इक्वल टू कैपिटल एक्स है कि स्मॉल एक्स है?
कौन सा?
ये ऊपर जो लिखे हैं U इक्वल टू,
You see if a dash is there in the X in between.
ये सर ये कैपिटल है कि स्मॉल है? ये
small x.
स्मॉल एक्स फिर ब्रैकेट में कैपिटल एक्स माइनस कैपिटल एक्स.
No, in the last one, like here, you are saying for here, like in this.
Yes, sir. Yes, sir. Yes, sir.
It's a notation for deformation field. First one, first X is.
Okay.
First is a notation. In bracket is a capital X.
Okay.
Okay. Got it?
Yes, sir.
Where is in this thing? If I am putting a dash mark in between the X, it's a small x.
Okay, sir.
Okay.
Yes, sir.
Got it? So now we have to find the U in terms of material form. So we need to convert the small x into capital X vector. Only then we can find in the material form. So now, what is small x in terms of capital X? It is x only, capital X.
Yes,
okay.
Sir.
What is small y in terms of capital? Here in deformation field is y plus az. And what is small z?
Small g is equal to z minus
ay, capital Y. And what is this
yes.
capital X vector?
Capital X vector is equal to
is nothing but xyz.
X y g. Yeah.
So now this U is in terms of material form. All things are in capitals. No small is there.
Yes, sir.
So now we'll do
Yes,
simply
sir.
vector subtraction. It becomes 0.
Yes, sir.
It becomes az.
Az is
And it
become
becomes
minus ay
nice.
plus ay.
No, minus ay. No. Z
No,
minus ay
minus.
minus z.
Okay, sir.
So this is nothing but displacement in
Displacement in material form.
good. So you got this thing, no?
सर एक मिनट मैं इसको नोट कर सकता हूँ, एक मिनट.
Yeah, take 2 minutes you take.
Okay, sir.
So this is the generalized problem I am solving. Like in one problem I will be solving the 5 subparts. Okay. To get
Yes,
you
sir.
more clearer understanding.
X y z u equal to 0 z सर हो गया. Okay, y. Sir,
Okay. So till now you understood the point. Okay.
yes, sir.
Now second part in this question only. U in terms of spatial form.
Yes, sir.
Okay. Now in material form, we converted the small x vector to capital X vector. So now in spatial form, what we have to do? You have to convert the capital X vector to a small x vector.
Small x vector.
So how you will do it? Since this deformation field is a one-to-one function, we can take an inverse of this.
Yes, sir.
And we can represent our displacement vector like this. So how you will do it now? This thing. So now this is small x.
Yes, sir.
This is small y. This is small z. Okay.
Yes.
Now
Yes, sir.
capital X in terms of small x is capital X is equal to small x only.
Yes, sir.
As per the given deformation field.
Yes.
So capital X becomes small x.
Small.
Now what is capital Y in terms of small y?
Small y.
This is nothing but capital Y is equal to small y minus AZ.
AZ.
But you cannot write in the format because capital Z is also there. You want all in terms of small.
Yes, sir.
Okay, so now you have to use this equation also. Here capital Z is
small g
plus AY.
plus AY.
Okay. Now you put this capital Z in this equation. What you will get?
Yes, sir.
Capital Y is equal to
capital Y is equal to small y minus a
small z minus AY.
AY.
Got it? So now taking this into right hand side, this AY term, so capital Y becomes small y minus small z upon 1 plus A. You got this thing?
Yes, sir.
Okay, now this capital Y is related to all the small terms.
Yes, sir.
So now we can write in the matrix this vector that it is small y minus small z upon 1 plus A.
1 plus A.
Now we have to write capital Z in terms of small z. So now we know capital Y. So we'll put the value of capital Y in this equation. A into small y minus small z upon 1 plus A. This thing we put here.
Yes, sir.
Got it?
Yes.
So now what is capital Z becomes?
Small g plus AY plus.
Do you get this thing? You get this thing or not? See, here we write this capital Y in terms of small y. So y minus AZ. Now here we write capital Z as small z plus AY. Got it?
Yes, sir.
Now we substituted the value here. We did one mistake. Here, when we substitute this capital Z to here, it will become AZ. Y minus AZ minus A square Y. Not getting it?
Yes, sir.
Now it's correct?
Yes, sir.
So it will become this. 1 second, one more mistake. It will become 1 plus A square in the bottom, Y minus AZ. Now this is correct?
Yes, sir.
1 second. Someone wants
Sir,
to
small y
raise this call.
Yes, sir.
One second. So now this capital Y is correct?
Yes, sir.
Similarly,
यहाँ भी सही करना पड़ेगा ना सर?
yes.
कैपिटल वाई को
Yeah.
हाँ
So now we'll do again this thing. Now capital Z is small z plus ay, a capital Y, and our capital Y is
yes sir
small y minus a small z upon 1 plus a square.
a square
Correct?
yes sir
Now if you do all the calculation in denominator and do this thing, you will get what you will get. We'll do 1 plus a square into small z plus
Yes,
a small y minus a small z upon 1 plus a square.
yes sir
So it will nothing but z plus ay upon 1 plus a square.
yes sir
So we'll write here
hmm
okay.
yes sir
So this is what our u in terms of spatial form. 1 second. First of all, one new attendant joined, Devo Prava Mahato. Are you able to hear my voice, Mahato? Am I audible, Mahato? I guess he's not able to listen. Okay, okay.
yes sir
Okay. So what we are doing, Mahato, actually, we are just solving a sample question here. So when I will post the YouTube link, you can go back and see it. Like, I'll give you just a brief now. Like this is a problem. Like we have given a body. Okay. Now what is a body? How it is going? It is represented. I have explained in earlier part of my lecture. And now this is a deformation field given for the body. So in the first part, it has been asked like we have to find a displacement vector in both material and spatial forms. So this is what we are finding. So in this first part, we have written like what is the deformation field given to us. So now the question asks, now the displacement is given by this relation. You can see in this in the video lectures given in the week 2, or you can see my lecture in the initial parts I have explained like how this u comes like small x minus capital X. The small x we refers as current configuration and capital X we refers as reference configuration. Okay. Now going to the question, that first thing is asked like u in terms of material form. So material form he is asking like we have to find a displacement in the reference configuration. So we change the small x into capital X with the help of deformation field. So now how this small x related to capital X we have wrote, this small y is related to capital Y plus capital Z, and this small g is related to Z minus AY. And we separated with the reference configuration vectors like x, y and z. Now in both the equation all the capital terms are there, so we do the normal vector law of vector subtraction. So finally we get this thing. This is nothing but the displacement vector in material form. Similarly, when next step it is asked like u in terms of spatial form. So since the deformation field is a one-to-one function, how it is one-to-one function I explained in the earlier parts, you can see. So we just do the inverse of the deformation field also to relate the small x. Okay. So now u in terms of spatial form will be written like this, as the equation says. So now this small x vector we can write like this, small x, small y, small z. The basic idea is that if it is asked in the material representation, you have to put all the capital X, capital Y, capital Z. And if it's asked in spatial form, you have to use all the small x, small y and small z. Okay. Now we subtracted with the deformation field. Now here capital X is related to small x. Okay. So we simply write it small x here in terms of capital X. Now this capital Y is not simply related to small y. We need to do some calculation. So now capital Y is small y minus AZ, A capital Z, and capital Z is small z plus capital AY. So with the help of certain mathematical calculation like shifting the Z value to the above value and do the calculation, we got to find that our capital Y is nothing but small y minus a small z upon 1 plus a square. Similarly, capital Z is small z plus ay upon 1 plus a square. So till now we are here. Okay. So Anna, you got the thing, how to got the
Yes, sir.
displacement field in material form and in spatial form.
Yes,
Okay.
sir.
So like U in material, what we got? Zero comma AZ minus AY.
Minus AY.
And U in spatial form, what we got?
0.
0. Just check the mathematics also, okay? I can be wrong. Okay, just check the mathematics, okay? Just for the speed purpose, I can be wrong in somewhere for mathematical calculation. Just pardon me for that thing. I will try to do as much correct as possible, okay?
सर इसमें कुछ चेंज नहीं हो रहा है, सिंपल ही वैसे ऊपर जैसे मतलब हो रहा है वैसे ही लिखा जा रहा है.
See, in top, it is written as material form. You can see like it's capital X
Yes,
and
sir.
capital Y. So suppose if someone asks you, like see our point has occupied like 5,0,1 in current configuration.
Yes, sir.
And he says that I will give you the relation like how to relate current configuration to reference configuration. Just give me the point of my body in the reference configuration. So how will you do that thing? You have to do with this method only. Or he will say like, okay, I will give you the current configuration coordinates and I will give you the deformation field. Just tell me what is the displacement of my particle in reference configuration. So if they say that give me the displacement of the particle in reference configuration, you have to use this for our case, this example. And if they say like tell me the displacement of my particle and current configuration, you have to do this thing. Okay.
सर मैं अपने जैसे मैं समझाऊं, मैं एक बार आपको बता रहा हूँ अगर वो सही है तो. सर जैसे आप ये स्फेरिकल फॉर्म निकाल रहे हैं.
यस, स्पेशल.
सर हाँ, स्मॉल y इक्वल टू अगर सेम वैल्यू दिया हो तब 0 हो जाएगा, अगर वैल्यू चेंज होगा तो वही लिखा जाएगा.
यस,
जो वैल्यू है वही वैल्यू लिख देंगे.
यस, अगर सेम होगा जैसे स्मॉल y इक्वल टू कैपिटल Y होगा तब.
हाँ, तब तो
then it's not a difference. See, if small x equal to capital X, small g is equal to capital Y, both the points in our coordinate system will place at same point.
Yes, sir.
So there is nothing technically, no difference.
Okay. अगर सर यही स्मॉल y इक्वल टू स्मॉल y रहेगा तो वो वैल्यू 0 हो जाएगा.
Yes.
Okay, sir. Okay, sir.
Got the point?
Yes, sir.
So now moving ahead, in the second part of the question, it is asked determine the location. Now your answer will come like this. Determine the location of the particle originally at 1, 0, 1. He said like originally the particle is placed. It says like find the location of the particle originally at 1, 0, 1. So he has given us the coordinates. Okay, but we have to find out the location of our particle at that point. Okay. So originally means what? Originally means is reference only. Okay, reference configuration only.
Okay, sir.
Okay. So what are the, as per capital Y, capital Z and capital X, what are the location of our particle as per deformation field? Is capital X, capital Y plus AZ,
yes sir,
capital Z minus AY. This is what given?
Yes sir.
Okay. In our problem. So what is the location of our particle at 1, 0, 1? Just put the value.
Yes sir.
1, A, 1. This is what the answer is. Got the thing?
No, sir.
No. See, he said determine the location of our particle at point 1, 0, 1. Okay.
Okay, sir.
So our particle at reference configuration is given like this as per the question only. See, this deformation field is very important, whichever is given. Okay.
Yes, sir.
So, 1 second. So in reference configuration, what are the positions of our particle? It's nothing but capital X, capital Y plus AZ, and
Plus
capital Z
AZ.
minus AY. This is what given in the question.
Yes, sir.
Now he said, as per
सर
your
ये नहीं समझ में आ रहा है ये कहाँ से 1,1,1 आ जा रहा है ये नहीं समझ में आ रहा है.
Okay. So he said to determine the location at 1, 0, 1. It means our X value is capital X value is 1, capital Y value is 0, and capital
1.
Z value is equal to 1.
हाँ.
Just put in our case.
1. Okay, sir. Okay, sir.
You got it? How this
Yes,
1,
sir.
1 comes?
Yes, sir. Yes.
So in the question he said like capital X, capital Y, capital Z takes the value of 1, 0 and 1 respectively. So as per your deformation field, you tell me the location of your particle in reference configuration. Okay. So in reference configuration,
Yes,
my particles in X, Y, Z are respectively as X, capital Y plus AZ and capital Z minus AY. So now I put the values of capital X, capital Y, capital Z and find out the location.
Yes, sir.
Got it?
Yes, sir.
Understood? Mahato, are you able to get it? You can type it if you are not able to open the mic. Okay, meanwhile we'll proceed. So now next part comes here. Next part it says in the question that now he says determine the location of the particle
In the reference configuration
of its if its current location is 0.5, 0.5 and 0.5. See, with the question itself you can understand like he says like now your small x, small y and small z are having values 0.5, 0.5 and 0.5. Okay.
Sir, current location मतलब small x, small y and small z.
Yeah. This is given. So what is the location of a particle in reference configuration? He is asking. Okay. We'll see how to do this thing. So he says like our small x is equal to 0.5, small y is equal to 0.5 and small z is equal to 0.5. Okay. This is what it is said.
Yes, sir.
I will check the question. Yeah. And he said you have to find out what is capital X, what is capital Y, and what is capital Z. This is what he is asking. That determine the location of a particle in the reference configuration, given that the current location of the particle is 0.5, 0.5, 0.5. Okay.
Yes, sir.
So small x, small y, small z is given. He's saying find me capital X, capital Y, capital Z. So to find these things, initially in the first part we found out that capital X is nothing but small x as per the deformation field.
Yes, sir.
We calculated. Y is nothing but small y minus is AZ 1 plus A square.
Yes,
and
sir.
capital Z is nothing but small z plus AY plus 1 upon A square. This is what we calculated.
Yes, sir.
So now what you have to do? You have to put the values of small x, small y and small z. So what your capital X becomes? 0.5.
0.5.
Capital Z becomes 0.5 minus A into 0.5, 1 plus A square,
Yes, sir.
and capital Z becomes 0.5 plus.
0.5 plus A 0.5 1 plus A.
So this is the answer.
Yes, sir.
Simple.
Yes, sir.
Understood?
Yes, sir.
So just you have to see the question, what it is said. Like read the question carefully while solving assignments and in the quizzes. Okay. Okay. See,
Yes,
in the
sir.
C part, he said like current location is given. So whenever he uses the term current location, it means small x, small y, small z. Okay.
Yes, sir.
Now he is saying
Yes,
just
sir.
find the location in the reference configuration. So what it means? You have to find capital X, capital Y, capital Z. Okay.
Okay, sir.
Now we'll go to D part. He said determine the displacement of the particle originally at 1, 0, 1. Okay. So now what he said, like in D part, he said like he is given the capital X, capital Y, capital Z values 1, 0, 1. Okay. And he said find displacement in reference configuration. ओके
सर ये क्यूज और असाइनमेंट सर एक ही नाम से आता है
क्या चीज हाँ सेम ही है
अभी
हाँ एग्जाम में
आप जो
हाँ
बोल रहे थे
सेम एग्जाम में आएगा वो ओके मैं बाई मिस्टेक मैंने वो बोल दिया जब एग्जाम दोगे तो उसमें क्वेश्चंस रीड करके ही आंसर करना कि विच लोकेशन इज गिवन करेंट लोकेशन इज गिवन और रेफरेंस लोकेशन इज गिवन एंड व्हाट इज आस्क्ड ओके so here they ask like displacement in reference configuration. Okay, so initially in first part we found out what is displacement in material form. This is
यस सर
so u is nothing but 0 comma aj comma minus ay if I'm right. Yes, so you have the points capital X capital Y capital Z at 1 0 1.
यस
So what is u?
यस सर
0 comma a comma minus a comma 0
माइनस ए
no 0 y is 0 no
यस सर यस
y is 0 okay. So this is your displacement in reference configuration. Now you got it. Whatever you are asking like how it is changing, why we want these things.
ओके सर ओके
So now coming to the last part, it says like determine the displacement of the particle currently at 0.5 0.5 0.5. Now you solve and tell me the answer quick. I'll give you 3
सर
minutes.
एक मिनट क्वेश्चन दिखा दीजिए
I'll give you this is a question. Determine the displacement of the particle currently at okay just to tell me what do you mean by currently at 0.5 0.5 0.5.
स्मॉल एक्स स्मॉल वाई स्मॉल जेड
Yeah, it is given. Fine, good.
यस
Now
और
what
सर
is the
वो जो
displacement?
उधर जो हम लोग निकाले हैं सर स्मॉल वाई इक्वल टू स्मॉल एक्स कैपिटल एक्स और स्मॉल वाई इक्वल टू ए
This thing,
यस सर उसमें
this thing we found out. Just is put the values and get the answer.
यस सर एक मिनट सर
Okay.
यस सर
Use the equation. Tell me the answer.
एक मिनट सर 0.5
Mahato, you can also do like I know you just missed the initial part of the lecture, but use this equation, put the values and get the answer. Just be comfortable with the lecture, okay?
सर सेम ही आएगा
No.
अरे सर 0.5 माइनस ए 0.5 1 प्लस ए स्क्वायर इससे पहले जो हम लोग निकाले थे वो सेम ही आएगा वही तो बोल रहा हूँ
Okay, okay, okay. You are comparing with the previous question. Yeah.
Yes,
Then it will
sir.
come same. Yeah.
यस सर
Okay.
यस
So what is u? I'll just solve for the other people who will see the lecture afterwards. Like we have given small x, small y, and small z equal to 0.5, 0.5, and 0.5. Okay, and u we have calculated earlier in the earlier parts in as in spatial form. So now putting the values we will get 0, 0.5 minus a into 0.5, 1 upon a square,
यस सर
and finally 0.5 plus a into 0.5, 1 upon a 1 plus a square. Okay,
Yes,
So
sir.
this is the one simpler problem you will see in the deformation field. Okay,
Okay, sir.
this will cover your assignment, like half part of your assignment, with different set of problem, not the same type of problem. Okay. Now coming on to the second question. This is similar to the first question, but little bit tricky, like just changing the words. Okay. Now here they have given you the default like displacement, and they are asking you tell me the small x, capital Y, in terms of these other things. Okay. So how you will do it? We'll see. First we'll read the question. A unit cube is subjected to the following deformation displacement field expressed in material form. What do they mean by material form? The meaning is the U is related to capital X, capital Y, and capital Z. That is what given in the question also. You can see this thing.
Yes, sir.
So now then they are saying that capital X, capital Y, and capital Z denote a typical material particle in the reference configuration. That is what I said you have now.
Yes, sir.
Now, the component of the displacement undergone by a same material that is occupied the point 0.5, 0.5 and 0.5 in the reference
0.5.
configuration.
Yes, sir.
You have to find out.
Yes, sir.
So what you will find out here?
सर पहले तो ऊपर जैसे ऊपर का निकाले थे इस रेफरेंस पॉइंट और करंट पॉइंट
Yeah.
उसको निकालेंगे
Yeah.
और उसके बाद सर
Simply in such questions, what you have to do like that, you have to find the relation between small x and capital X. Nothing like that. Okay.
ओके सर
If you will see like what is given here, we are given ux this is what given. One check. This is given. Okay. So whatever the problem is given to you like this, you first do in a stepwise procedure. Like what is u? U is nothing but small x minus capital X. This is what we learned so far.
यस सर
So you put one by one each equation. So what you will put? You put ux. So 0.5x plus 0.1y is equal to small x minus, sorry, this is not the vector now, small x minus capital X. Okay. So now small x becomes 1.5x plus 0.1y.
0.5 सर 0.5 ना
This will go here, no?
ओके ओके सर 1.5
Got it?
यस सर
Now you will write uy 0.05y is
Yes,
equal to small y minus capital Y.
कैपिटल वाई तो
So small y will become,
1.05
now you will write uz this 0.1z,
यस सर
small z minus capital Z. So small z will become
1.1 जी
Now you can, while seeing these three things, can you relate the first problem? Now this is nothing but deformation field.
यस सर
In first question, we have given a deformation field. These three things were given. In first question,
ओके सर
this small x, small y, small z are related to capital X, capital Y, capital Z. And we find out displacement and the location. Now here, in second question, we have given ux, uy, uz. And with the help of this relation, we have found out the relation between small x and capital X, small y with capital Y, and small z with capital Z. Now you can able to solve the question as we did in the first one. Like, what is the location of the particle when in the reference configuration? Like location of particle in reference configuration at 1, 0, 1. How you will do it? Just tell me.
What is location?
See here, location reference configuration is capital X equal to 1.
Capital X, yes sir. Capital Y 0 and capital Z is equal to 1.
In our deformation field, how it is given? 1.5x plus 0.1y.
Yes sir.
1.05y and 1.1.
Yes sir.
So now put the value, you will get the location.
Yes sir.
Got it?
Yes sir.
Okay, similarly, if they said in the current configuration, same thing, you just put, you have given the value small x, small y, small z. Okay.
Okay sir.
Now you got it, how to do it?
Yes sir. सर एक मिनट थोड़ा उसको नोट कर
Yeah.
हम ऊपर का नोट कर रहे थे इसलिए.
Okay, no issue. It's just that you are understanding the concept or not. This is what my basic motto is.
Okay sir.
You should understand the concept well so that you can able to do the assignment on your own. Mato, are you able to understand the things? If you can speak, I can able to understand you better. Like I will tell you in another way if you are not understanding in one way. See, the motive of this live session is to interact with me. Even if you are not understanding like twice or thrice, I will explain you. Nothing like that. My motive is to tell the topics which were covered in that week to be more clear to you. Okay. I'll just first tell you the concepts, then I'll solve you the example so that you just understand what is the concept and what are the problems which will involve those concepts. And this will help you in doing the assignments also. So written?
Yes sir.
Okay. Now finally in the lecture, in the final parts of the lecture of week 2, the professor has told you about the tensor algebra and basically the stress. Okay. So I won't go much into the deep of that things. I'll just basically define what is like tensor. I'll just tell you few concepts and we'll solve the final third example. Okay. So tensor. You know what is scalar? You say like scalar is dependent on magnitude only. And you say that vector is dependent on magnitude and direction. Okay. What is this magnitude and direction means in our world, in the world of mechanics? Is nothing but invariance. And what do you mean by invariant is that if you map the thing in different Cartesian coordinates, these things won't change. Suppose if you say that I am mapping a scalar quantity in my system, my Cartesian system, and suppose you are mapping the same scalar quantity in different Cartesian system, which thing will not change? The answer is magnitude. So that is why we say that scalar quantities are those quantities which are dependent on the magnitude only. You got my point? Enough?
Yes sir.
Similarly, vector. See, suppose I will say like I'll map a vector thing in one Cartesian coordinate system and say like another person is mapping into another Cartesian coordinate system. So which thing will not change? The magnitude of that vector and the direction of that vector will not change. Okay. Similarly, in tensor is nothing but what we'll study is a second order tensor. In this, it involves three invariants, which you will be learning in the subsequent weeks. The definition of a second order tensor is nothing but it maps. It's a linear mapping basically. I'll correct myself.
Sir, एक बार और tensor बता दीजिए.
Yeah. See, the scalar is nothing but a zero order tensor. Okay. I'll show you. You will learn these things better in next subsequent weeks also. I'm just covering the basic thing. Okay. It's a zero order tensor. Vector is first order tensor.
Okay sir.
Okay. Now you say like scalar is nothing but dependent on magnitude, which deals with magnitude only, like mass, temperature, These are all scalar.
Yes, sir.
So what is this magnitude means? Why you say magnitude always? Why not another thing? Because if I map a scalar quantity in one Cartesian coordinate system, E1, E2, E3, I say this is a scalar quantity. Suppose hypothetically, I'm saying, okay. And another person comes, he said like I will map in different Cartesian coordinate system. One second. E1 star, E2 star, and E3 star. So what thing will not change? In terms of scalar, magnitude will not change. These things will know called as invariants. Invariants are those things which are independent on the Cartesian coordinate system. You are getting?
Yes, sir.
So in vector, what are the invariants? Magnitude and direction. Okay.
Okay, sir.
So whatever you suppose this is a vector point. This is the vector point I have drawn. Okay. Suppose some other person mapped this vector point in E1, E2, E3 space, and another person mapped this vector on E1 star, E2 star, and E3 star space. So final conclusion for this vector is that whatever the Cartesian coordinate system you follow, its magnitude and its direction will remain the same. Okay.
Yes, sir.
Similarly, tensor, what we'll study is second order tensor. Okay. In higher syllabus, we'll study fourth order tensor also. But for this course, we study only second order tensor. Why? Because stress strain are all second order tensors.
Yes.
Okay. In second order tensors, there are three invariants. Okay. These all things you will study in week 3, I guess. Okay. It's just for the rest of thing, I'll just introduce it here. Okay. So the definition of second order tensor is nothing but a linear mapping between two directed line segment. What do you mean by directed line segment? In first week, sir has defined vector as a directed line segment. So it's nothing but a linear mapping between two vectors. Second order tensor. Okay. So how we will denote this thing? We'll denote this thing as, suppose y is a vector, A is a linear mapping in X. Okay. X and Y are vectors and it is mapped with the help of A. The double dash means second order tensor. Wherever you see double dash, it means second order tensor. Okay. Single dash means vector and no dash means scalar. This notation you have to keep in your mind in going further in your engineering or whatever you are doing. This notation will help you in seeing the question and understand the question. It's just the starting for your career. Okay.
Okay, sir.
So learn this habit of writing these things, because if you like say like, oh no, I will not, like I just simply like remove like this simply A, you will not understand the value of these things. Okay.
Okay.
So A underscore double dash means second order tensor. So Y and X are linearly mapped with the help of A, which is known as a second order tensor. Okay. You can see the lecture for more mathematics involved. I'll just simply write like this A tensor is nothing but Aij EI crossed with EJ. This is the formula of a general second order tensor. Okay. You can go to the week 2 lecture 7. Okay. To understand all these things better. Since I have a time constraint, I have to go fast for this thing. Okay.
Okay.
So an Aij is nothing but vector tensor A EJ dotted with EI. How this is coming are all explained in the lecture. Okay.
Okay, sir.
Okay. So now I'll say we'll go to stress. Okay. So in the lecture, to define a stress, the professor has first told you about traction. And traction is nothing but a distributed force over a cut surface or a boundary surface. distributed force acting on a cut surface or a boundary surface. Okay. Did you watch the lectures whole as of now?
No, sir.
No. How you are getting this? How will you get these things?
सर
See,
एक्चुअली सर इसका
हाँ.
क्लास भी किए पड़े हैं ना.
So, but are you getting what is section? Did you learn before what is section is?
Yes, sir. Little more.
Okay, then I'll do something more to have a better understanding. Otherwise, simply solving question will not help also. Okay, some basic background knowledge should be there. Suppose we have a body like this, potato shape, and many forces are acting like this thing, this thing, this thing, and this is a support. By the way, you know what is supports are? What is this support called? This support is known as hinge support.
Hinge support, yes, sir.
And this support is as fixed support.
Fixed.
Okay. Oh, sorry, I'm writing surface. Okay, suppose this is a body. Hypothetically, this is a body. Okay, and several forces are acting at point A, B, C the support, D the support, and E. Okay. Now I have cut a body. See, suppose we define always stress as force upon area, but this is not an actual definition. This definition holds true for specific examples like a uniaxial tension or compression. But when you go ahead, this definition doesn't hold good. Okay. So to define a stress, first we need to define a traction. So suppose we cut a body into half, not in half, anywhere we'll cut a body like this. So now if I see this body like this, with forces acting like this, this is support. So when you cut a body, you will see a distributive force which will act like this. One second. So this distributed force
yes, sir.
acting over a cut surface.
सर तो ये बॉडी कट होगा तो इसका पार्ट वाला भी तो फोर्स लगाएगा ना.
हाँ, this is nothing but the Newton's law of motion. Every action has an equal and opposite reaction.
Opposite reaction.
So दोनों में equal and opposite forces लगेगा. Distributed. Okay. So the distributive force acting over a cut surface. This is distributive force. It is acting on a cut surface or a boundary of a body. This is called as traction.
Okay.
Okay. You can see in the lectures also, sir has defined beautifully that thing. Okay, I'm just covering a summary of that thing. Okay.
Okay, sir.
Okay, so traction depends upon number of things. It's a function of number of things. F denotes function t, x, and n. So what is t? T is nothing but time. What is x? X nothing but a position of the particle. And n depends on the normal to the surface. Okay.
Yes, sir.
First two terms are, you have seen in previous examples also how position changes will change the location and all these things, and how time will play a role. At time equal to t0, the body is in reference, and time t equal to t, some other position is there. Now what is this n? See, suppose I'll give you a body like this. One second, I will draw correctly. And the P force is acting like this. Okay. Now I'll say I'll cut body in two ways. This two. Now what will you say? At this point, when a body is cut, like in vertical and in a slant point, will the traction be same?
Yes, sir.
See, in this cube, you say. So suppose I'll tell, like we cut this cube into half by a vertical line, this line. One way to cut this cube is one. Another way we cut the same cube in second type, in a slant way. So will the
No, sir,
traction
traction same नहीं होगा.
or the stress will be same? But as per your definition of force upon area, it will be same.
Yes, sir.
So that is where the difference comes.
Okay, sir.
So orientation plays a role. Okay. It depends whether where you are cutting the surface, in which orientation, which is a normal to the surface, their position. What is the location of the particle? Suppose this is a thing, this is a cube, and moment is acting like this.
Yes,
M.
sir.
So the stress distribution, if you will see like this, it is like this for this same body. Okay.
Yes, sir.
So if you want to calculate stress at this point, it will be different.
Yes, sir.
If you want to calculate at this point, it will be different.
Yes, sir.
So here the position will play a role. Got it? So that is what traction has been defined. You will get to know more these things in the subsequent lectures. This is for the overview. Okay. So now that you understand traction, you can see the lectures for better understanding. I'll just define what is stress now. Okay. So first, traction is nothing but sigma transpose n. This sigma is nothing but stress. Transpose means you know transpose, how to take a transpose of a matrix.
Sir.
Okay.
Yes, sir.
And double dash means
Second order.
very good. Second order tensor.
Traction.
And what is this n? Is n is the normal to the surface.
Normal to the surface.
Okay. One more small concept I'll tell you. See, if we write sigma, it will be like sigma 11, sigma 12, sigma 13, sigma 21, sigma 22, sigma 23, sigma 31, sigma 32, sigma 33.
Yes, sir.
Okay.
Yes, sir.
So what is the sigma 11 means? This first thing will denote the normal surface.
Okay.
And the second thing will denote the direction of force. Okay, I'll tell you with the cube example. So suppose I'll focus on this plane. Okay.
Yes,
okay. So then this surface I'll define the coordinate system as y, x, and z. Okay.
Okay, sir.
So here, if I say this thing, this is ex. Okay, x direction. So and traction is acting like this. Tex. Okay, normal to the surface. That's pointing outward. Okay.
Okay.
Normal to this. You're getting a plane, and outward normal. Is Tex traction acting. So the stress here will be sigma xx or sigma 11. Why? The normal surface is x. This.
Yes, sir.
And the direction of force is also along the x direction.
X direction.
So it will write as sigma xx or sigma 11, whatever you write. Okay. Now I say this here.
Yes, sir.
What will you say? See, our plane is x plane.
Yes, sir.
Direction of force
Y direction.
So our x
In Y direction.
is a normal surface and the direction of force is
Y.
So we'll write sigma xy or sigma 12.
Yes, sir.
Similarly here also.
Okay,
is sigma x
Z direction.
or sigma 13.
13.
Suppose I was doing for this plane. So what will be this? Sigma y, because the plane is y, direction is y.
Y.
Sigma y. Okay, got it? So in this plane, this is sigma y, plane is y, direction is
X.
Got it? This is
Yes, sir.
plane is y, direction is z. Got it?
Yes, sir.
So you now got the understanding like what is sigma 11 means, how
Yes,
the
sir,
value
yes.
is. For better understanding and better clarity, you can go to lecture and see all these things. Okay.
Okay,
Now
sir.
we'll solve one problem. See, this is the problem. I'll just paste it in another page. Okay, this is a problem. So it says that the stress state corresponding to an orthonormal Cartesian basis. Now, what is orthonormal Cartesian basis? This Ex, Ey, Ez. These are all orthonormal. Why? Because dot product of either of them is 0 and with oneself is 1. Okay. These are orthonormal to each other. Okay.
Yes,
This is what the meaning of orthonormal Cartesian basis. So the stress state is given in this thing. Okay.
Yes, sir.
And question is asked, represent the stress on the stress cube.
Yes.
So we'll draw a cube.
Yes, sir.
You just tell me the directions, okay? Now
Yes,
I
sir.
want you to say. I'll draw the Cartesian system for a second. This is y. This is x. This is z. First of all, tell me what is sigma xx here in the system, in the question.
Sigma xx is equal to minus 10.
Very good. What is sigma xy?
Oxy is equal to 5.
Good. What is sigma yx?
0.
No,
Sir,
yx.
0,
5.
10.
5. See this thing.
Sir, ये y हो जाएगा
No, yy is this.
2 or 1. Yes, sir. Sorry. 5.
Okay.
Y is equal to 10. Yes, sir.
So now you know this. What is sigma xx? Now where to draw the line for sigma xx?
Sir, boundary. मतलब y direction.
See, this is x plane.
Yes, sir.
Okay.
X plane में.
X plane in the direction of x.
X.
Now outward or inward?
Sir,
See, plus means outward. Towards the positive direction.
Minus.
Negative means towards the inward direction of whatever you define the coordinate system. Okay. See, in our coordinate system, this right hand side is a positive side. Okay.
Okay.
So now this minus 10 represents this thing. Am I correct?
Yes, sir. Inward.
Similarly for other side also.
Sorry.
To make it a full thing. Okay.
Yes, sir.
Now what is sigma xy?
Xy is equal to 5.
So where to draw?
Sir, out.
Like this?
Yes, sir.
Downward?
Yes, sir.
Why yes, sir? I did wrong.
सर आउटसाइड होगा ना सर तो आप इनसाइड कर रहे हैं
नहीं वो होगा हाँ very good हाँ this is what I will do some deliberate mistakes also okay don't say yes every time
okay sir
so this is correct
yes sir
5 okay now other side 0
yes sir
other things so we don't know need now this plane now y plane is given to us so what is sigma yy 10
sigma yy is equal to 10
where to put inward or outward
sir outward
sure
yes.
correct
Yes, sir.
and 5 sigma yx
sigma yx is equal to sir outward
this thing or this thing this one or 1 or 2 1 or 2 where to draw
sir 1
correct pakka
yes sir
this is positive where is the positive x in 1 or 2
positive x sir
see this is 5 no positive
yes sir
see your plane is y direction is x so where is the positive direction 1 or 2
एक sir wait 1 minute sir
this
2
is the correct 2
yes.
good
Yes, sir.
okay just understand the meaning of these things okay first means plane second means direction okay and you can draw it got it
yes sir
now in second question they said you have to find a traction t of n
सर वैल्यू दिया है पुट कर देंगे
Yes. So T of n is sigma transpose n.
and
So sigma we have, it's given in the question, and n they said is
direction
ex plus ey
NEZ
ez by root 3.
√3.
So just put the value, get the answer.
Yes,
10, 5, 5,
5.
minus 10. Sorry. This one is 1 by root 3. 1 by root 3. 1 by root 3. What you will get?
Sir, EX is equal to minus 10.
Root 3 plus 5 by root 3.
Yes, sir.
Here 5 by root 3
10
plus
by
10 by root 3. Here 0.
0.
Got it?
Yes, sir.
So this covers all the problems required for you to do in the assignment thing.
सर ये
And the
आंसर है
concept, huh? What?
सर ये दूसरे वाले का आंसर है
Yeah, this is the answer.
EX plus EY plus EZ.
Yeah. See, this is the find the traction acting on the plane whose normal makes an equal angle with the coordinate basis. So we define traction. What traction is? Sigma transpose n. So we did a transpose and we did multiplication, matrix multiplication. You have find out. Okay.
Okay, sir.
See, for better understanding of what is traction, how it's working, how it's dependent, what is stress, what are the inside mathematics involved in a tensor, you can go through the lectures. What I have covered is a summary of all these things for you to solve the question and get a better understanding. So far in all the 3 problems I have solved, did you find any difficulty?
No, sir.
Are you able to solve all these things?
Yes, sir.
So see, if you can solve these things which I have solved today, you can be able to do assignments clearly and understandably. Okay. Okay.
Yes,
Any
sir.
feedback for today's lecture? Like you want me to improve on something, or you want me to give more examples, or you want me to cover other things?
I can मतलब मैं बहुत अच्छे तरीके से इसको समझ पाया.
Okay. Good. I feel really good like you like these things. Mahato, did you able to understand like whatever I have covered so far after your joining? It's better if you tell like in chats or you can open your mic. Mahato. Okay. So that's all for today's live session. Like I have covered all the examples required for you to solve in the assignments and all the topics covered in week 2. Okay.
Yes, sir.
I hope you watch all the lectures. Okay, to get better understanding. See, without seeing the lectures, you cannot get an in-depth knowledge because I am here for like 1.5 hours to 2 hours. Okay, and I have to solve the problems also, make you understand also, and I have to cover topics in a summary wise. So the better is in that question,
पूछ रहा था तो मैंने इसको चैट बॉक्स में डाला है उसको कहाँ अपलोड करें मतलब discussion forum में कर दे कि
discussion forum is the best thing to put the question because other than me faculties will also be there.
Actually मैं वो क्वेश्चन कर चुका हूँ आपसे बस पूछना था कि सर वो तरीका जिस तरीके से लगाया
you have my number no WhatsApp number you just posted me in the WhatsApp. I'll do this thing, just note down this number. Mato, you can also note down. If you have any doubt in the question you can ask me. See, before assignment due date I won't give you the answer, I will only tell you the procedure. Okay
sir. Yes, sir.
What is the procedure required? My motive is that you have to learn properly all these things. Okay, not to give you the answer. Okay, I'll explain you the topics.
Yes.
Okay. So any questions, any doubt regarding anything so far covered in this lecture?
No, sir.
Okay, then I'll take your leave. Thank you for coming to this live session. Thank you, Anna. Thank you, Mato.
Thank you, sir.
Bye.
Bye, sir.